Assuming this is recording and what is on my screen is actually being recorded and will be appearing on your screen, you should be seeing a big black rectangle at the bottom with some numbers and a couple of words and arrows and some lines sticking up from it. This big black rectangle has a top surface that is flat, level, horizontal and, well, not planar because it's just a line rather than a surface, but think of it as a cross-section through something with a planar upper surface. The markings are equally spaced, representing 90 degrees south, 80 degrees south, 70 degrees south, 60 degrees south, 50 degrees south, yada yada yada, the equator, 10 degrees north, 20 degrees north, yada yada yada, 90 degrees north, also known as the North Pole. Sticking up from these, I have some lines. Red, orange, yellow. It's kind of dull yellow, so it shows up against a white background. Green, cyan, blue, indigo, and violet. Yes, this is a gay pride diagram. Actually, it's just distinctive colours. Hey, gay rights are human rights, I don't mind. Anyway, that's not what this is about. This is about stars. It is fairly well known and widely accepted that there are points on any line of longitude where certain stars will, at the time of year when they're visible, pass directly overhead. If you are 89.34 degrees north of the equator, then at some point during the night, the very long nights that you get that far from the equator, you will see Polaris directly overhead. Of course, sometimes it'll be 1.32 degrees away from directly overhead on the other side of the North Pole, but sometimes it goes directly overhead. Likewise, if you are at 50, I think it's 57.20 degrees, could be 56 point something, I forget. I looked it up at the time. If you are at the correct latitude, Merak, one of the two pointer stars of the Plough constellation, part of Ursa Major, is going to be visible directly overhead. Now this is outside the Arctic Circle, so this is a seasonal star, and is not necessarily visible when directly overhead at all times of year. Here we have 38.78 degrees north, Southern European, not quite Middle Eastern. The latitude, well, the declination of Vega, and the latitude of a set of points on Earth at which Vega, at some point, is seen directly overhead. Again, at the correct time of year. At some times of year, at exactly one time of year, Vega will be directly overhead at midnight for whoever happens to be at the correct longitude, to be on the midnight side of the Earth at that time of year, as the Earth goes between the Sun and Vega. Later in the year, the Sun is farther around, sunset comes later, midnight comes later, and Vega will already be past overhead, west of overhead by midnight, and will set to the west before morning. Still later in the year, Vega is only briefly visible, just after the sky gets dark enough for you to see it, and before it disappears behind your western horizon. Then it's only overhead during the day and not seen at all, and then it's briefly visible in the early morning, after it appears above the eastern horizon and before the sky gets too bright at sunrise. And then you get back to when it's rising in the middle of the night, disappearing overhead in the morning, to being visible all night and overhead at midnight again. Same applies to Orion. You won't get much of a view of Orion in June. November, pretty visible. Here we have a green line for Bellatrix. I think is 6.35 degrees north. Orion's lead shoulder. The bright blue one. The dull red one that follows along behind is Betelgeuse. Ipfelgauser, the armpit of the hunter. Yes, great language. Great name for a star. And then farther south you have Orion's Belt, 3 stars, Anitak, Anilam, Mintaka. From left to right, if you're in the north and looking south at him, Mintaka is the lead one and is 0.30 degrees south of the celestial equator. So here we have the substellar point for Mintaka marked in cyan, 0.3 south. Just 3 pixels left of that 0 mark. Then you have his sword or dagger hanging down with the lovely nebula in it, in this gap between cyan and blue. Blue is for Regal, which is his leading knee or foot, depending how he's drawn. And then behind that you have Saif, which actually means sword in Arabic, but is generally his other knee or foot. And then following along behind him is his faithful hunting dog Sirius. And this indigo line here is the substellar point for Sirius. 75 degrees south. Way to the south of that, we have at 23 degrees south, we have the Tropic of Capricorn, and the north coast of Australia is roughly there. All the way down here at 52.70 south is a violet line for Canopus, one of the most visible, one of the most prominent, brightest, shiniest, most obvious stars in the southern hemisphere. And then down here there isn't a line at 90 south because there isn't a star at, isn't a naked eye clearly visible star at 90 south. There is just the south celestial pole, which you'd have to take a star trail photograph to identify. So based on given these latitudes and these stars, of course, let me zoom right in and go across to the other end. If you are not 89.34 degrees north, but 90 degrees north, right at the North Pole, Polaris won't be straight overhead, ever. It'll always be 0.66 degrees from overhead, which is why this line coming up from my 90 degree north mark is sloping 0.66 degrees left. If you are 60 degrees north instead of whatever that latitude is, your line of sight up to Merak won't be straight up, it'll be, if that's 56.5 degrees as an arbitrary, this will be 3.5 degrees south of, directly overhead, when Merak is at its closest to overhead. 50 degrees north, your line to Polaris is 49.34 degrees right of overhead, that's this red line coming this way, and your line to Merak is 6.35 whatever degrees north of overhead. I say right again, north to Polaris. Meanwhile, your lines of sight to Vega are of course south of overhead, these dull yellow lines. There's one there and there's one there, until you get down to 40 north, and then there you have 38.78 north, where it is directly overhead. Anywhere south of there, the yellow line from 30 north is 8.78 degrees north of directly overhead. You may notice there are an awful lot of lines on this image. There really are. I have drawn in lines, Polaris in red, Merak in orange, Vega in yellow, from 90 north and from 80 north, and from 70 north, but from 70 north also the green for Bellatrix. And then from 60 north, all of them plus this cyan line for Mintaka. From 50 north, all of them plus the blue line for Regal. From 40 north, I've added the indigo line for Sirius. Same again at 30 north. Then at 20 north, there is no red line for Polaris, because from 20 degrees north, Polaris does not get 25 degrees above eye level. And that's down into haze and muck and light pollution and refraction being a really big issue So sod it, basically. Again from 10 north. Then from the equator, Canopus is finally high enough to get its violet line added down here, which just wasn't worth doing anywhere north of the equator. We get to 10 degrees south and we lose the Merak line. There is no orange line to Merak from 10 south because too near to eye level. Ditto at 20. From 30 south there isn't even a yellow line. We're only looking at Bellatrix and southern stars south of Bellatrix from there. And so on south. You'll notice that from 30 south there is this red line. This red line here is pointing at the south celestial pole, because you can work out where it is in a star trail photograph and then, calculate that elevation angle. And as we go south, same again, and then at 60 south we stop bothering with Bellatrix. 70 south we also stop using Mintaka. At 80 south we don't even have Regal, and by the time you get to 90 degrees south all you've got are Canopus and the South Celestial Pole. All of these lines, showing the elevation angle of the stars at their nearest to directly overhead in the course of the night, they should intersect. If you have a bunch of positions, let's get back to the equator here, you have observers at the equator and 10 degrees south of the equator and 10 degrees north of the equator, all pointing at Mintaka as it goes directly at its nearest to overhead. And you get the angles at which they had to point at Mintaka, and you get this sound line that's sloping up on the right, this sound line that's sloping up from the left, this sound line with very little angle in the centre, and you follow them up and you find that they all cross just there. That spot there. Obviously drawn at a scale of 0.69 miles per pixel. There's a limit to how accurately you can plot that. But you get that position. The thing is, that's a rather short base when you have observations extending all the way out to 60 north and south for Mintaka. And likewise for all the others. If you have a green line to Bellatrix at 70 north and a green line to Bellatrix from 50 south, why would you only use the ones from the equator and 10 north? You can just use them and you'll get 1 point. But two lines that crossed a very shallow angle like that, you get this very long intersection where it's hard to be sure of the altitude. If you get your lines to cross at more like right angles, take this 60 north line up here and the 30 south line, they're crossing pretty much at right angles somewhere in this tangled mess of strings. And that gives you a much tighter position, much tighter lock on the position of an object. Military analogy, if you can hear where the enemy's mortars are and you can draw a line on the map to them, and somebody else does that from a very different position, you know where they are. But if all you've got is two sides of the same bunker, your two lines are pointing in pretty much the same direction, and they take a very long time to cross each other, and you know what direction the mortars are in, but you don't know how far. Or it could be the radio signals from, say, the Bismarck, bragging about his glorious victory over HMS Hood for rather too long and giving people time to get really good, accurate bearings to him. If your bearings are from 2 points far enough apart, you know where the Bismarck is. If they're from the same, two sides of the same naval base, you only know roughly what direction. So we should be using these lines from as far apart as we can, as well as the substellar point. And you get this problem. That right there in the middle of the screen now is a pair of sound lines crossing. So that is a calculated position of Mintaka. Over here is another pair of sound lines crossing. That's another calculated position, and there's one there, and there's one there. And there are several there, and there, and more on the way up to here, and all the way up there they're crossing. And there, and there, and there. All these different crossovers, and the same applies to green, and to blue, and to indigo. Over here we have the same thing with violet. We have these TP shapes. Yellow, orange, and the red at both sides. Looks a bit like a quilt hanging over a slack line. We have all these different positions, you know. If you work it out from the North Pole and the substellar point, Polaris is anywhere in that single pixel vertical line. If you work it out from the North Pole and 80 North, it's somewhere at the bottom of that line in that single pixel piece where the two cross. But if you use 70 South, it's somewhere down here. Unless you use 70 South and 70 North and 80 North, in which case it's just off to that side a bit. Let me zoom in so I can put them in the center of the screen in case the mouse cursor isn't showing. That whole single pixel vertical red line, that's your North Pole and substellar point. That little bit in the middle is your North Pole and 80 North. This cross in the middle of the screen is 80 North and 70 North, but this bit up here where the line sticks out, just before the line sticks out to the right, is North Pole and 70 North. Then here you've got North Pole and 60 North, and here is 80 North and 60 North, and down here is 70 North and 60 North, and here's North Pole and 50, 80 and 50, 70 and 50, 60 and 50, but if you use North Pole and 30, you're all the way down here, and if you use 60 North and 30, you're across here, and if you use 20 North and 30 North, you're down here at this single pixel here. That's a bit of a mess. Zoom back out a little, and we can see other problems, such as this green cross here. This one. These are two lines of sight from 70 North and 60 North to Bellatrix, and they cross there. So the Bellatrix observed from those two latitudes is apparently at this position. See that dull yellow line just to the left of it? That's the substellar point at 38.78 North for Vega. Well, anyone who's at 38.78 North can tell you they're not seeing Bellatrix north of Vega. They're seeing Bellatrix all the way over here. And if you use your 70 North, was it? And there, sighting to Bellatrix, and they're sighting to Bellatrix, you get Bellatrix all the way up here, this point. Way higher and way farther south than this point. See the problem? Meanwhile, anyone who's south of the equator is going to insist that Bellatrix is somewhere over here. So we have this cluster of observations, but they don't quite line up. They're kind of all over the place, and the more latitudes you observe from, the more all over the place you get. It's kind of hard to distinguish these. Maybe I should have used the colours out of sequence to get more contrast. But here you go. Here's a purple cross, an indigo cross for Sirius. And here to the left of it is a green cross for Bellatrix. These two observers tell you a position of Bellatrix. These two observers tell you a position of Sirius. And those two calculated positions are the wrong way round. You've got Bellatrix south of Sirius. That's bollocks. And if I zoom out, you can see all of these, the red quilt hanging over a slack line to each side, and the rainbow of TPs in the middle, and this whole thing is bollocks. Something has gone very wrong, either with the logic, which we can confirm from real-life observations, or with the geometry, which is probably right, because I did win the maths prize too, twice at one of those difficult schools to get into with an actual, entrance exam. I've drawn all the lines horribly wrongly. Now I'm sure I've drawn some of the lines wrongly, but all of them seems unlikely. Or something about that black rectangle at the bottom is wrong. Fortunately, this isn't a single image. This is a composite of a lot of layers. I have a layer for the black rectangle, a layer for the text, a layer for each of these vertical lines for a substellar point, and a separate layer for each set of observations. There is a layer for 90 north, a layer for 80 north, a layer for 70 north, a layer for 60 north, a layer for 50 north, and so on. Which means I can copy just the observation lines from each latitude, including the substellar point as a single observation line from a single latitude, and rotate those layers by their own latitudes. I could rotate them by 1/10 of their own latitude, or 1/5, or by twice their own latitude, but that would still be bollocks. But if you rotate them by exactly their latitude and you move them so that the single pixel, I'll show you a single pixel, right down to this observation here at 30 north, this single violet pixel here that is the bottom ends of all those lines, it's almost a full rainbow. It's an indigo line, not a violet. That single pixel there gets moved to coordinates that are 100 sine 30 to the right and 100 cos 30 up from an arbitrary center point somewhere near the bottom center of the image. And that single red pixel there, they do alternate because I drew them alternating red to violet, violet to red, red to violet, violet to red, gets moved to coordinates that are 100 sine 40 to the right and 100 cos 40 up from that same center. And way across here the equator doesn't get rotated at all, this set of observations, and that gets positioned just 100 up from that center point because sine 0 is 0 and cos 0 is 1. And this dull yellow pixel gets 100 times the sine of negative 10 degrees, which is negative 100 times the sine of 10 degrees to the right. In other words, 100 times the sine of 10 degrees to the left of that center point, and 100 times the cosine of 10 degrees, which is equal to 100 times the cosine of negative 10 degrees, up from that same center point. And this pixel here, the bottom of the substellar point line for Mintaka, gets put 100 times the sine of negative 0.3 degrees to the right of, and 100 times the cosine of negative 0.3 degrees up from that same center point, and so on. We get that. And like I said, I'm sure I drew at least 2 of those lines incorrectly. Possibly I drew them correctly, but then rotated them incorrectly. This software can be a little weird about rotating layers sometimes. You forget to press enter. But the result is a bunch of red lines all pointing exactly to the left. There we go. All those lines to the south celestial pole, as determined by star trail photograph, are all pointing in the same direction. All of these lines to Polaris at the closest it ever gets to overhead from any latitude from which it can be seen within 65 degrees of directly overhead, are all pointing in the same direction, 0.66 degrees above, straight to the right. All these orange lines, they're all pointing in the same direction. All these yellow lines from the latitudes at which Vega can be seen near enough overhead, they all point the same way. And all the green lines all point up this way, all in the same direction, as if, well, Apart from this one over here, apparently. But the ones that I didn't screw up all point in the same direction, exactly as if, as a certain kind of Harry Potter fan might say, there's only one Bellatrix. All those sound lines, they're all, apart from that one. I really did screw up rotating some of these layers. They're all pointing at the same place. You have one Polaris at a vast distance off to the right of this image. You have one Merak at a vast distance up and right from this image. One Vega, a vast distance up and right, just in a slightly different angle. One Bellatrix, vast distance off the top of this image and significantly to the right of it. One Mintakar, vast distance away, very slightly left, 0.30 degrees left of, straight up from this image. And one South Celestial Pole, at an infinite distance to the left from this image. And then, it all makes sense. So to draw all of these angles from a flat plane, well, you have to draw all the angles from 80 degrees north from a flat plane that is just a few meters wide and rotated 80 degrees from the orientation of the flat plane a few meters wide at the equator. You can treat the Earth as, you know, a bunch of flat 1 meter triangles, and within observational and experimental error, it'll work just fine, like this. But if you do treat the Earth as being a whole load of 1 meter triangles rotated, you know, according to latitude and longitude, such that star angle observations work,